这个下面放杯，好。
首先呢，我就介绍一下今天晚上我们讲座的这位专家教授，是 Professor Brian Wynne sorry 那么 Wynne 教授呢是来自于英国兰开斯特大学的科学学教授，他是兰开斯特大学和卡迪夫大学的一个联合的基因组学、经济社会和伦理问题研究中心的副主任。同时呢威利教授还是兰开斯特大学气候变化研究中心的主任，以及应用系统分析国际研究所的研究主任，欧共体联合研究中心的客座研究员，英国科学学和科技政策研究中心主任，以及呢英国皇家学会的顾问小组的成员，英国上议院科学技术委员会的成员，以及英国首相科学技术理事会的成员。那么威利教授的 background 就是他的学习经历呢都是在剑桥大学取得的硕士和博士学位。下面就请我们用热烈的掌声欢迎威利教授。
谢谢。I'm sorry that's as far as I can go in Chinese. So I just want to first of all express my gratitude to Professor Lei and colleagues here at the University of Huanchong who've invited us to speak to you, and my gratitude also to you for having come and also to have asked to hear me speak in English without translation. I hope that you can understand me well enough, and I'll do my best to speak slowly and clearly. But of course, as you will see, as my lecture goes on, I get engaged with my thoughts and material, and I get animated, and I speed up. So I must look for signals from Professor Lei or from you to remind me to slow down and keep my voice clear, to give you a chance to understand me. But thanks anyway for attempting to hear this lecture in English, and I apologize that I can't speak to you in your own language. The title of my lecture is Public Engagement with Science, Rethinking Science-Public Relationships in Europe. Europe has been probably one of the most significant arenas globally where science-society interactions have come into difficulty of various kinds and for various reasons in recent years, the last 10 or 15 years or so. And of course, this is also the period of time that new powers, including China, have emerged globally into leadership in fields of science and technology. So that in addition to the issues which arise around why have we got various problems with the public reactions to science in Europe, there's also a lot of concern about globalization and in particular the global competition, often called the global science race. Notice the global science race. We have a race along a single track. The implicit assumption being then that there's only one direction only for the whole of global society to go in with science, technology, and so on. So there is also anxiety, as reflected in this quotation, which I take from a recent speech by the British Prime Minister, Tony Blair, about UK science spending and about how we have to keep maintaining and accelerating our support of science in order to keep competitive with new nations. And you see here China mentioned as one of the leading competitors for Britain and indeed other European nations in investment in scientific research and development in order to keep ahead in the global race, as it's called, for innovation. And other developing countries like India are also mentioned in this same kind of framing of these issues. So, now then, let me see if I can. I can't get it to move on. Just trying to. Excuse me, no, it's just not moving. See if it, okay, yeah, let's try it. Where is it? Yes, is this through? Yeah, it's gone back to this one. Yeah, it's okay. No, it's okay. Yeah, that's the one I want. It's okay. Yeah. No, we've lost it now. Yeah. Sorry about that. So, I've just listed here some of the issues which have arisen in Europe since about the 1980s, the last 20 years or so in Europe. Some of the issues involving science very centrally, in issues which have encountered controversy for various reasons. You can see here, for example, nuclear power, which has been a continual source of public controversy since the 1970s. And in particular, the nuclear fuels reprocessing plant near to our university at Lancaster, at Sellafield, as it's called. GM crops and foods, genetically manipulated crops and foods, has, as you probably know, been a big issue in Europe and a source of a lot of conflict with the United States over the US's complaints to the World Trade Organization about Europe's so-called moratorium on imports of US GM crops and foods. In 1994, there was a big controversy when the environmental group Greenpeace actually took over an oil platform, a drilling platform, which had been used in the North Sea, was being decommissioned, and was being towed to the North Atlantic for disposal by just dumping it on the ocean floor of the North Atlantic. Greenpeace actually invaded and took over the oil platform whilst it was being towed by Shell, its owners and users, for dumping. The dumping had been authorised by the British government, the risk assessments had been done, and Greenpeace invaded it. The media were on the case very quickly, publicised it very heavily, and consumers of Shell petrol began to vote with their feet, as we say, by boycotting Shell petrol. In other words, they voted in favour of Greenpeace and against official science, which said there's no environmental risk from the dumping of the Brent spar on the ocean floor. And one of the significant points about this controversy was the way in which the definition of the issue was assumed to be the risk assessment of one oil drilling platform, the Brent spar. In the North Sea, there are between 400 and 500 such drilling platforms, more of which have now been decommissioned. But Greenpeace's concern, and indeed the concerns of many members of the public who voted with Greenpeace by boycotting Shell petrol, was that, well, if we allow this one first oil platform to be dumped on the ocean floor, what will happen with the 400 or 500 other such oil platforms when they are decommissioned? They're likely, if the first one is dumped on the ocean floor, to go the same way. So what is the risk assessment question? Is it the risk assessment of one platform only, or is it 400 to 500 such platforms? A very different risk assessment question. What is more, we knew, and we know still, that there is a lot of nuclear waste from British military and civil nuclear programs which was scheduled for dumping on the same Atlantic Ocean floor in the 1980s. And this was only stopped by the Seamen's Union in Britain joining forces with Greenpeace, who lobbied them, to actually prevent the dumping of that nuclear waste. The government then didn't know what to do with the waste, so they simply stored it in the harbours, awaiting some resolution of the issue. So that also could have ended up being dumped on the ocean floor. The controversy was actually about how do we frame the science of risk assessment. It wasn't just a factual question alone. Are the risks too high or too low? The question was the risks of what? One oil platform or 400 to 500 oil platforms, plus possible other things too. And for risk assessment science, that is always a question. Okay. I wonder, can I try this? Okay, I don't know whether that's better, but let's see how it goes. I'll have to lean forward to try to make it. So, the Brent spar controversy illuminated various other more general issues about environmental risk assessment, which also, in fact, fed into the controversies around GM crops, where the issues of environmental risk and how we frame the scientific questions about environmental risk are still now, after 12, 15 years later, are still alive and unresolved. In the mid-1990s, at the same time as the Brent spar controversy was occurring, there was, of course, the mad cow disease issue in Britain, with the question about whether the epidemic of bovine spongiform encephalopathy, I won't try and translate that into Chinese particularly, BSE, as it's usually called, or mad cow disease. The question was, will this disease, could it spread to humans? The scientists said no possibility. And there were various other models, ways of thinking about this, which actually, and indeed empirical evidence, which showed that the infective agent had jumped the species barrier before, so it might jump the species barrier again from cows to humans, consuming the infected beef. So that was another big issue where public trust in science and public suspicion, public belief that science was being manipulated politically by the politicians and by industry and so on, was very strong. So it contributed yet further to a general sense that science was being framed, was owned, controlled, and used in ways which were not accountable, not transparent, and not trustworthy, not operating in the public interest. Various other controversies again which are listed here, I won't go into the details of them all, but all of these contributed to a sense that we need to examine science much more carefully, much more accountably, and we need to have public involvement in these processes. In Britain in particular, but also in the rest of Europe, there are very active non-governmental organisations, often scientifically well qualified these days, unlike 30 years ago when some of them began, which wasn't really the case. Nowadays they're scientifically pretty well qualified, so they know what questions to ask of science in these issues. The media are very powerful and very active, and they often conduct campaigns for themselves for commercial reasons. So all of this contributed to a sense of strong public scepticism and mistrust of science used as public authority for important policy decisions with safety and other issues about innovations like GM crops, like nuclear power, chemical pesticides, beef hormones, milk hormones, and so on and so forth. This also resulted in investment in a lot of research on public attitudes. Often with the assumption, the belief on the part of many of the people funding that research, that the reason why there was a lot of public resistance to government decisions in favour of things like GM crops was because the public is ignorant of science. Now, we can take for granted, I think, that the public is ignorant of science by and large. Scientists are also ignorant of science. My doctorate, my PhD is in materials science, physics of materials. I stopped studying biology when I was 15 years old. And when we began to study biotechnology in the 1990s, I had to climb up a very steep learning curve of biology and genetics and so on, even although I had a doctorate from Cambridge University in physics of materials. Scientists are also ignorant of science. The point is, that doesn't necessarily have a causal effect. It doesn't necessarily cause rejection or opposition to science. And that assumption of that connection has been made too easily and too widely in these kinds of issues. Whenever there is public opposition, it's assumed that that opposition is because of public ignorance of science. So, in the year 2000, the United Kingdom House of Lords Select Committee on Science and Technology conducted an inquiry lasting a year into the state of science and society relationships. They took evidence from a lot of witnesses, scientists, social scientists, NGO activist people, government officials, various others, academic researchers too, and they concluded there was indeed in the UK a big problem of public mistrust in science, albeit selectively, discriminating mistrust. It wasn't blanket, but selective according to what the issues were in given domains. But this report
Sir, you have to talk to the mic.
Sorry. Yeah.
Probably you can hold it, or you can sit down.
It's fine. Maybe I'll just try it here again, but lean down a bit. Yeah. Okay. Yeah. So this report of the UK House of Lords Select Committee in 2000, Science and Society, officially pronounced that these, what were called deficit models of public opposition to scientific innovations like GM crops or innovations promoted by science, this report officially buried those kinds of official explanations of public opposition. It said that public opposition is often based upon different kinds of reasons than public ignorance. In fact, the surveys of public attitudes, like there's a big survey in the European Union funded by the European Commission called the Eurobarometer report. It's a barometer, in other words, of public attitudes towards things like biotechnology and other areas of science and technology. The Eurobarometer report itself showed in the mid-90s how there was no correlation between levels of public ignorance in science and attitudes, negative attitudes towards science. If anything, it showed that there was actually a correlation of an inverse kind between levels of public ignorance and attitudes towards science. The more educated that people appeared to be about science, then, not surprisingly, the more questioning they were about science. So, this report officially buried those so-called public deficit models, and it called instead for a new culture in science and policy of two-way dialogue instead of the attempt to achieve public consent by educating publics one way into the science of genetic manipulation or nuclear energy or anything else. And the UK government, the European Union governments, and major institutions like the British Royal Society and the Wellcome Foundation and so on, backed this call. And that has really been the source of a major commitment made in Britain and in Europe, in the European Union, towards what's called public engagement with science, meaning public dialogue, that not only should publics learn from science, but also science should learn from publics. About, for example, what questions should they be asking about issues like the Brent Spar, for example, and its environmental risks. So, when we ask the question about understanding public reactions to science, the first question we really have to ask is, what do we mean by science here? Science and research are two different things. So that, particularly since the 1950s, science has been institutionalized extensively in all parts of the world, but particularly in the developed world, in Europe, North America, and so on. It's been institutionalized as public authority. Advisory committees, expert advisory committees, on almost every topic under the sun have been established in order to advise governments about decisions on energy, on chemicals, on agriculture, on health, and so on, and so on, and so on. There are so many scientific advisory committees now in every national government in Europe and around the world that they're almost countless. And these advisory committees, so-called, are effectively decision-making committees, because ministers, who are the scientists are advising, very, very rarely go against, refuse the advice which they're given by those scientific committees. They're routinely advising, but actually making decisions on behalf of government and the people that are electing those governments into being. So the institutional science, which is now established as authority in so many fields of public policy, has become a field of government in its own right, and has been studied in that way by many scholars in my field of science studies. But that kind of institutional science is very different from science as we think of it in research, at the research front of different fields, in university laboratories and various other kind of institutions where research is carried out. Advisory scientific bodies operate under certain legal criteria and conditions which allow them to ask some questions, but do not allow them to ask other questions in formulating their advice to governments. Scientific research, thankfully, doesn't operate according to such kinds of directives. So that when we say science, do we mean science as institutionalized in the form of policy advice, or do we mean science as operated and practiced at the research front in the variety of fields that exist? When we talk about scientific knowledge, do we actually mean the promises which are made in the form of sincere expectations about things like a cure for cancer, or the postponement of aging, human aging, infinitely perhaps? These are sincerely held expectations or promises on the part of scientists, but they're not empirically demonstrated scientific knowledge. So what do we mean when we refer to science in these kinds of domains? Do we mean these promises, which are effectively fictions, not facts? Or do we mean empirically founded, factual knowledge? These are ambiguities. They're not resolved. They're left open. These meanings are not clearly stated and resolved when we're referring to science as authority in these domains. So there is a question that arises. Well, if we encounter public opposition, public concern about a new field of innovation, science and technology, what is it that we think the public is reacting to? And this is something that I want to actually spend some time on in the coming minutes of this lecture. We can't understand public reactions unless we first ask, well, what is it that we think they're reacting to? What is the meaning which they have, the public has, when it's reacting in these ways which we find problematic, mysterious, inexplicable, or whatever? And so I'm a social scientist nowadays. I left material science a long time ago, and I spend a lot of my research time trying to do research on public attitudes, including to issues like GM crops and foods in Europe. And I find myself, as a social scientist, attempting to represent public attitudes, or the reasons why publics have attitudes of this kind or that kind on issues of that sort. Earlier, I did similar work on nuclear power and public attitudes to that. And when this kind of social science is representing publics, then we're representing publics' forms of reasoning to scientists, to government officials, to policymakers. And as such, we're also playing a policy role. And we have to take responsibility for that. We can't pretend to be sitting back only passively observing the world of science and policy and public reactions which is going on out there, as if it's in a goldfish bowl separate from us. We are in that world too, making our observations, and those observations count. So we are also, in that sense, actors in those policy worlds. And we have to take responsibility in that way. Now, one of the main areas, as is clear from the issues which I've listed and talked about, where public concerns over science have arisen, has been around the general field of risk. Arguments have arisen about the risks of nuclear power, chemical pesticides, triple vaccines for children with mumps, measles and rubella, mobile phones, toxic wastes, GM crops, beef hormones, milk hormones, and so on and so forth. The list is almost endless, where controversies have arisen about the risks from this or that or another scientific or technological innovation. So that it appears as if the arguments and the issues are about risk alone. What are the risks? Are they too big or are they small enough to be acceptable? And this is usually the way in which scientists who've become very influential for good reason in these kinds of areas have assumed that the only issue is indeed the risks. And it's worth just stopping here to think about, in regulatory processes where risk assessment is used in advising governments about innovations of this sort. The common sense, reasoned way of doing this is to say, well, okay, we find out what the risks are and we balance the risks against the benefits. So we trade risks against benefits. That's the reasoned way of doing it. If the benefits are too small and the risks are too high, we say, no thank you, not worth it. If, on the other hand, the benefits are high and the risks are small, then we say, fine, let's do it. Good idea. It's a good thing for society. Now, what we notice in these kinds of regulatory processes using risk assessment, in all of the issues that I've just listed and described there, and many more, the question of benefit rarely arises. And it's worth just stopping to ask, why is this true? Why is this the case? Then we realize when we think about it that actually the reason is because within liberal capitalist societies, the assumption is that if anybody, an individual, a corporation, a government agent perhaps, who wishes to promote something for regulatory decision, then the assumption is that by definition there is a social benefit. There's no question. If anybody wants to promote something for commercial sale in society, by definition the social benefit is shown. That's it. If it sells, it's a social good. That's been the definition of benefit. So it hasn't been a question in the regulatory process. And that's led to some big problems in many of these kinds of issues. And I think it's one which Europe, anyway, is returning to question whether it shouldn't actually introduce what's called a fourth hurdle question in regulatory processes. Fourth hurdle meaning a fourth hurdle in regulation in addition to the three prior hurdles. First one is efficacy. Does the innovation work in the way it's supposed to? Second question is health. Is it going to create a health risk? Third question is environment. Is it going to create an environmental risk? And the fourth question is, what's the social benefit? Because even if the answer to all of those three questions is fine, is okay, if it's not going to generate any benefit, then it might still not be worth it. What's the point of doing it if it's not going to generate benefit. And this is where these processes are at the moment, in this kind of evolutionary process, where we're realizing that actually we haven't systematically raised those questions about benefit before, and maybe we need to see where this would lead. But when we ask the question, well, public reactions to science, and as I've pointed out, we need to ask, well, what do we mean by science, first of all? That's what I want to spend some minutes on, first of all, before we return to the question, how do we understand public reactions, and what do we mean by the process of public engagement with science in ways which would not shut down scientific activity. The first point about the shifts in the nature of science in the late 20th century is the one that I've already described and listed here, the first of these bullet points here, which is that science was institutionalized relatively recently. We think of the science as having begun in the 17th century in Europe, and, other civilizations would claim a lot earlier in their own situations, like China, for example. But if we think of European science as having developed since the 17th century in Europe, it's only in the last half century, the last 50 years, that science has been institutionalized as public authority in the way that we now know it. In the way that I described earlier, making decisions or giving advice on the acceptability of new technologies, which is now, of course, a central part of social and political and economic life everywhere in the world. But that authority role has only been there since the mid-20th century. We're still developing how that role is played, as I've just mentioned, with respect, for example, questions about benefit and how they should be related to questions about risk. So, one of the points which has not been really properly addressed or recognized in this 50 years or so of development of science's role in this respect is that the main role that was seen for science here was simply informing policy decisions. Is it safe or not? Ask science, we get an answer. The risks are thus. And then we make a decision as to whether those risks are acceptable, whether or not we go ahead and have the innovation or reject it. So that seems like a rational way of using science to inform policy decisions. We still have to judge what's an acceptable level of safety. That's a political and a social question, not a scientific one. Okay? So science informs policy. But we find, as we've moved into the 21st century, that actually by default almost, science has taken on an extra role. It's not only informing public policy, but it's actually imposing, or it's defining the meaning of public policy, which is a very different, significantly different role. It's not only telling us what the risks are, it's saying to us that it's only that question about risks which is the public issue, that there is no other issue that we should deal with in order to make our decisions about these things. So that public policy becomes just a propositional scientific question. Is it safe? And that's a form of instrumentalization of collective life by reducing questions about what might be the public good, how might we actually generate the best social welfare for those in the most need, reducing to a question of instrumental question of safety. So the question of ethics, of values, of public good has been gradually, imperceptibly almost, backgrounded as we've gone from the post-war period to the early 21st century, over 50 or so years, as risk assessment has become a central tool of policy making. It's effectively excluded all the other questions from the public policy arena. And this is, an issue that we haven't yet even properly recognised, let alone addressed and responded to in the field of science and public policy. There has also, of course, been a huge intensification of the commercialisation of scientific research, including university research. Supposedly, the independent republic of science, as US science policy people in the 1970s described it, science speaks truth to power. Science is independent, and it has the independence to be able to speak truth to power in the ways that power manipulates truth to try to gain its own ascendancy and advantage. So this was always seen as being the key role of science in the public interest. That science was a defender of the public interest by acting as a restraint on unbridled, uncontrolled power. By always insisting on asking the right questions of power. Nowadays, we're in a position where science has been so heavily commercialized, where the imaginations of what counts as an interesting and valid scientific question have become imbued with the need to promise to funders who will provide the resources for the expensive technologies which scientists need to do their research, that all kinds of serious ambiguities have crept in to that idea of science as the independent republic, self-governing with its own norms and its own organisational principles to make sure that it could actually generate independent, valid scientific knowledge, which could then speak truth to power, as that statement said. Commercialisation has actually rendered ambiguous that very idea. Some people would say it's simply destroyed it, that it's no longer, we can't trust science in that sort of way. And certainly in the research which many social scientists like myself have done on public attitudes to science, we find repeatedly that ordinary publics take for granted that science is always imbued with interest of one kind or another. And the important thing is not to look for the disinterested science, because you won't find it. The important thing is to make the interests transparent, so that then we can judge between them as democratic citizens. And we find that in public attitudes, quite a realistic sense of that commercial influence which has occurred on scientific culture, including even pure science, as I want to indicate next. A further point which is important here is that as the German sociologist Wolfgang Kohn and Johannes Weyer put it in 1989 in German Gesellschaft als Labor, society as laboratory, that innovation, science and technology no longer develop into social goods, social technologies in society by first developing the science, then developing pilot technologies which are tested under controlled, isolated conditions separate from society. And only then, after all of that testing and risk assessment has been carried out, is it then released into society. But the kinds of technologies and sciences that we're using and developing are so complex that that kind of boundary is no longer there. That inevitably, as sciences and technologies develop into social technologies to be used in society, they're still they're still full of uncertainties which actually need to be tested in society itself. And that's the sense in which these people are talking when they say society is the laboratory. We're experimenting even after all of the risk assessment and regulatory effort has been made to test these innovations in more controlled circumstances. Now, I'll just move quickly over this and just point to how this is actually an excerpt taken from a paper by Hans-Jörg Reinberger, who is now a philosopher of science, German philosopher of science. He was until recently a protein chemist. He used to make proteins and work on them in his laboratory in Berlin. And here he's talking about the genetic project. What is the genetic project as a scientific project? And he's making a very important distinction between the conventional view of science as being about the attempt to represent, in the case of genetics, what goes on at subcellular level in interactions between genes and proteins and other chemical molecular entities within the cell. He's saying, no, that isn't the project. It's not a process of attempting to represent subcellular processes at extracellular levels on screens or in places where we can see them at a larger scale than their subcellular molecular level scale. This is a project of using the cell as the technological laboratory. That we're actually intervening at subcellular level, at genetic level, as part of our scientific knowledge generation. And that is a project of manipulation and intervention, which is a technological project. So that we can't any longer separate the project of scientific representation, of understanding in the form of asking, well, what actually is the gene and its interaction with proteins, for example, and then representing that separately from the process of intervention itself, which is how we do our observation. The process of observation itself requires intervention, which changes what we actually observe. And this is Heisenberg's, in physics, this is Heisenberg's uncertainty principle. That the energy transfer in the process of observation is of the same scale as the entities that we're trying to observe. So the energy transfer involved in the observation process, small though it may be, at subatomic level, that changes what we're looking at, what we're trying to represent. So we can no longer be certain that we haven't actually altered the reality that we were trying independently to observe and represent. Now here, what Reinberger is talking about is a more systematic and more deliberate process of the same. That representing is always intervening. And what's more, as Reinberger describes it here, that intervention is then actually automated or programmed at the subcellular or genetic or genomic level. And this has major implications for how we think about public engagement and what we think public engagement is about. If you remember, I posed the question, what do we mean by science when we talk about public reaction to science or public engagement with science? What do we mean? Do we mean the conventional classical idea of pure science, innocent of any intervention in nature, merely passively observing and attempting to reconstruct and represent natural processes and behaviours? Or do we mean technology? Intervention in and manipulation of nature, with human purposes implicit and expectations implicit within that project. So, just to express and give you an idea of how this kind of classical model of science as independent of any form of intervention, as being distinct from technology, pure science or basic science is completely distinct in this classical view from technology. This is the British Prime Minister again, saying precisely that science is just knowledge. Science does not replace moral judgment, it just extends the context of knowledge within which moral judgments are made. But the idea that there might be human commitments already involved in the knowledge making before we get to the point of applications is not imagined or recognized in this kind of representation. We have pure facts, and only after we've got the pure facts do we allow the human values to be exercised in the pursuit of whatever human ends it is that we think are worth enacting. And this is why scientists are often defining themselves as completely innocent of responsibility with respect to technology. That we, the scientists, don't have responsibility for what society does by way of applications. That's society's responsibility, not the scientists, because we scientists only do basic research and basic science. We innocently understand nature, we don't manipulate it. Well, scientists like Reinberger are saying the opposite. They're saying, actually, no. If we understand new sciences like genomics and genetic engineering and so on properly, then we'll understand them as technological projects. And the term technoscience is used to reflect that kind of weaving together of science, scientific understanding with technological manipulation. So, there are some important intellectual or epistemic implications of these kinds of shifts. One of the essential features of the classic model, as expressed by the philosopher Michael Polanyi in the 1950s, also, by the way, the author of the term, the Independent Republic of Science, speaking truth independently to power, that Polanyi described the essential ethos of scientific activity as being about the tacit, developing and articulating and sustaining the tacit skills of intuiting, of intuitively sensing what lies beyond existing knowledge. If science, as it's supposed to be, is an enterprise of innovation and creativity, of creative thought, then in Polanyi's view, it had to sustain the ethos collectively within science of intuiting what lies beyond existing knowledge. And as we see in all of the issues that I mentioned, and in many others where science is used as public policy authority, then the question of what lies beyond is deliberately excluded. It's not just that by default it's neglected, it's quite systematically excluded and prohibited. What counts is what is known, not what might not be known. And that is a very important shift. It's a big cultural shift in the way that we understand science as public culture and public authority in these kinds of issues. And in that sense also, consistent with Polanyi's interest in and expression of the importance of what lies beyond, that the reflective dimensions of reason have given way to a purely instrumental definition of reason and science. That it's purely about extending control. So much so that many people have argued that that has become an end in itself. That by default, the end of that instrumental control has been more instrumental control. And then more, and then more, and then more. But when you ask for what human purposes, what might the social needs be for which we might try to develop more control, then those are often social needs which are actually invented and articulated, as it were, to justify the commitment to the extended technological control. They're made up after the fact, if you like. So, these kinds of cultural and social and ethical dimensions of knowledge production have been obscured in these processes by the influence of the classical model still, of the idea of pure science, innocent of technological intervention, and then applied science only after the pure science has been created. Now, pure scientific knowledge, or basic scientific knowledge, of course, is generated through technological projects. Historically, in physics and so on, thermodynamics was generated as a scientific theoretical innovation through the technological interest in developing the steam engine. And the experimental technological practice of developing the steam engine helped physicists to understand thermodynamics better. And that's often been the case in the history of science. So, of course, basic understanding increases. But does it come before the technological applications? Not necessarily. And yet that is how it's perceived in these processes. So I just want to, I'll come back to this. Just to extend further these observations about the changing nature of scientific knowledge. This is the 10-year vision begun in 2003, expressed in 2003, the 10-year vision of the main basic science research funding body in biology in the UK, the BBSRC, the Biotechnology and Biosciences Research Council. So this is a statement taken from the 10-year vision. Underlying everything in our understanding of biology and biomedicine and our ability to apply post-genome biology reliably are two major known unknowns. Firstly, we have no hint about the function of around a third of the genes in most organisms, and for most of the rest, only limited information. Until we understand the function of these genes in greater depth, we cannot understand the processes that go to make up a living cell, let alone a whole organism. And secondly, it has become clear that the mechanisms by which genes are kept off and on, gene switching as it's called, are much more complex than previously thought. Understanding the fine-tuning provided by such epigenetic controls will be crucial to the development of I'm sorry, I've just missed my word there. Of efficient tissue engineering and bio-nanotechnology. So again, here you can see this is the Basic Science Research Funding Council, which funds, as it calls itself, the science base in the UK in biology. But here you can see technological expectations and ambitions and purposes driving its 10-year vision of the basic sciences. That kind of technological application is already there in the imagination and definition of the basic science research programs. And I just want to continue in this vein with this is an excerpt from an article in Nature Biotechnology in October 2 years ago, 2004. The title of the article was called "Can Complexity Be Commercialized?" Now, complexity, or as it's now called in this field, systems biology, really developed. Systems biology has existed, some say, since the 1930s. But it's taken on a new force, a new influence, since the mapping of the human genome in 2002, 2003, when it was realized there weren't anything like as many human genes in the human genome as had been expected. On the so-called central dogma, one gene coded for one protein which created one trait in the organism, whether that trait be disease resistance, disease susceptibility, what other trait it might be. On that basis, it was expected when they mapped the human genome that they would find about 150,000, anyway, over 100,000 human genes in the human genome. They were surprised to find that actually it was about 25,000, and that number has reduced gradually as they've done further work. The latest estimate is about 22,000 human genes in the human genome. In other words, not enough human genes to sustain the central dogma of genetics. One gene, one protein, one whole organism trait. There aren't enough genes to do it. So something is more complex than they had assumed. That simple central dogma mechanism doesn't work. There has to be at the very least gene-gene interaction, which creates new forms of proteins, which creates new kinds of traits. And many epigenetics scientists will say it's a lot more complex than that. Proteins are also regulating genes, as well as genes regulating proteins. So there's a complex forms of mutual interactive regulation going on, and other things are regulating the proteins. Even physical parameters like pressure within the cell apparently causes changes in those kind of gene functions and roles. So the question for the scientists is, do we attempt to understand this new complexity from the bottom up, from the molecular level, genes, proteins and so on, up to the cellular and then the organismal level? Or do we attempt to understand it top down by starting at the cellular level or the organismal level, looking for whatever functional parameters are of interest, and then trying to drill down, as they call it, to the molecular level to identify what relevant molecular processes are which connect with those organismal traits. So this is actually a characterization of that top-down scientific strategy in systems biology. This top-down strategy allows scientists to selectively identify molecular development pathways in manageable numbers, as this quotation indicates. Rather than having to work with 30,000 or so genes and 250,000 or so different proteins, which just becomes impossible in terms of identifying patterns, holding things stable and so on, researchers start at the phenotypic or event level, the organismal level, and drill down through functional pathways to only what is important in a specific disorder, whatever the disorder is that they're trying to develop therapies for, because that disease phenotype is what they want to change. Again, you can see within the basic biological research there is a technological ambition, a perfectly legitimate, good ambition, which is to develop therapies for diseases. But nevertheless, there is a technological ambition shaping the scientific imagination in the basic research. And in this sense, we can see that science is not only an innocent pursuit of basic understanding, which is then and only then considered for application, but that imaginations of application themselves inform the very process of developing the basic scientific knowledge. In other words, there are questions about social or human ends, purposes, needs, built into the basic scientific knowledge processes. And these processes are not at all subjected to public debate in even all these new processes of public engagement with science that have developed since the 1990s. Because they've been focused only on risk. Now, risk as a scientific question is a question which is about impacts, consequences, after the technology itself has already been put into place and implemented. In that sense, In that sense, it's a downstream question. The questions about human purposes, about what are we imagining that we're doing this science for in the first place, are more upstream. They're about production. They're not about protection. Risk is about protection. Asking these questions about why are we doing it is asking questions about production. Why are we generating the knowledge in the first place? And what social needs do we imagine that we're trying to meet in doing that? And which should have priority? Which social needs should have priority? And who should be involved in those processes and negotiating that? That is a democratic question which shouldn't be confused with scientific questions, but it's one which at the moment is completely concealed in these processes of public engagement with science. So, if I just go back quickly now. When we ask, well, again, the question I began with, what are publics responding to when we talk about them as responding to science? Well, one of the first assumptions was, well, publics are obviously, it was assumed, publics are obviously responding to the risks. We scientists know the risks, we'll tell them. So the public should be responding to risk magnitudes. What's the size of the risk? How many people will be killed or injured? How many excess cancers with this chemical or that radiation, whatever it might be? That was the first question. People are responding to risk magnitudes. Then psychologists and others began to do research in the 1970s and 1980s. People like Paul Slovic in the United States began to do research in psychometrics, which indicated that actually people were reacting not only to risk magnitudes, how many people will be killed or injured, but also to risk qualities, such as, is the risk a risk which I myself control, or is it one which is just imposed on me, whether or not I choose to have it? So, an example of a risk which I might think of as controlling myself might be whether I choose to drive my car in order to go to work. Whether I drive safely, whether I drink before I drive, whatever else it might be. That would be a voluntary risk. I choose to enter into the risk or not, as the case may be. An involuntary risk would be something like the chemical pesticides which are in my food. I don't even know, certainly not while I'm in China, I don't know who the authorities are and what they've done to investigate how much chemical pesticide there is on the spinach which I might have eaten for lunch or whatever. Those are classic examples of involuntary risks, or the chemicals in the atmosphere that we breathe in Wuhan city when we go about the city. An involuntary risk. We don't choose it, it's just there. It's imposed by the authorities. We don't even know who those authorities might be. Now, in terms of risk magnitudes, when we adopt a risk at our own will, according to our own will, then we are prepared, and there's empirical evidence to show this, we are prepared to accept a higher level of risk if we think of ourselves as controlling it than we do when we are actually having that risk imposed on us involuntarily by someone else without us having any choice. So risk qualities matter, and there are a whole variety of different qualities. What is the historical trend? Is the trend of the risk increasing over time, or is it decreasing? Is the risk equitably distributed over populations, or is it inequitably distributed, so that some people get a lot of risk and others get very little risk? These are qualities which can't be represented in magnitudes, and people say they matter. And in my view, quite rightly, seem to me to be important dimensions of risk questions. But then there are responses to the technology as a whole. So that, for example, risk assessment of nuclear power assesses the risk of a nuclear reactor failing in some dramatic way, so there's a big release of radioactivity, like the Chernobyl nuclear reactor explosion in 1986, 20 years ago. The risk assessment is conducted on that part of the nuclear technology, but nuclear technology is a much more distributed, complex technology, and that reactor on which the risk assessment is done would not exist without there being uranium mines, transportation of uranium fuel, the concentration and purification of uranium fuel into reactor fuel, the transportation of spent fuel from the reactors when it's discharged to sites where it's stored. In Britain it's reprocessed. Reprocessing emits much more environmental radioactivity as well as exposing workers. It extracts plutonium, which can be used for nuclear weapons. So that you've got a whole lot of extra risks and questions besides risks which are generated by the reactor's existence. It's the same question I started with and I illustrated with Brent Spar. What is the question? Is the question the risk from this reactor on its own, as if it existed on its own, independent of all those other elements of what's called the nuclear fuel cycle? Or is the risk issue, and indeed the social issue, the question of the whole fuel cycle, which is a globally distributed networked technology? It's not just a single piece of hardware technology in a single site, well defined, usually actually relatively well managed. The question of that distribution, how vulnerable is the plutonium to maybe terrorist retrieval and use, for example? Then there are social and civil liberties threats, as well as conventional kinds of risks of death. So are publics responding, in other words, not just to the risk questions as defined by the scientists, but to the technology as a whole and their experience of it? And with GM crops, a very similar question arises as with nuclear, because whatever the risks might be as known to scientists of the environmental and health consequences of GM crops, there are then also unknown possible consequences. But there are also social questions about the security of a global food supply system which is controlled by perhaps 5 or 6 private corporations globally, with intellectual property rights which prohibit farmers from doing their own experimentation on their own seeds and their own seed combinations in their own environmental and other soil conditions and so on. So there's an issue about food security if it's actually concentrated in the hands of 5 or 6 global private corporations. That question does not appear in the risk question, but it's a big question. And it's a question about the concentration of knowledge, because farmers are experimental practitioners in these situations. And if they're prohibited from that experimental practice, then that's a big social and indeed ethical issue. So these are questions which can't be divorced from the risk question. And they're not strictly scientific questions alone. So when we ask, well, what is the public responding to? Is it responding to the science alone? Or is it responding to this richer, more realistic, more comprehensive definition of what the issue might be? And when scientists and public authorities define issues and insistently define the issues as being only about risk, and that public reactions when they occur are only about risk as well, then this is where we arrive at some of these issues lower down in this list, 5, 6, 7, 8 here. In other words, are the authorities imposing on the publics alien definitions of their concerns by insistently saying their concerns are only or should only be about risk and not about the other social and other questions which I've defined? So when we ask, well, what are publics responding to? Social research of a more qualitative, open-ended kind, which allows people to articulate their concerns in their own terms, with their own meanings, often indicates that actually people are concerned about risk as a relational question. In other words, they are concerned about their dependency on institutions that they don't feel they can trust. They know they are inevitably dependent upon those institutions, but they don't feel that they can trust them. And that's a situation which is a very unhealthy situation. This is called public mistrust in science. It's not really public mistrust in science as such. It's public mistrust in the way that science has been institutionalized in processes of innovation, of government decision-making and policy, and in industrial research and development. And in that sense, public engagement with science has got to be about opening up the processes such that these wider issues become more open and accountable democratically, whilst leaving science to define, or not to define, but actually leaving science to pursue scientific knowledge within its own terms, so that one doesn't want to confuse the scientific laboratory with the democratic agora or the arenas of debate and negotiation. But there is an issue here in the public engagement with science domain, which is about attempting to articulate a capacity institutionally and democratically, but also in policy for science, to articulate a capacity collectively, and I mean globally. This is not just a European thing, but I mean globally. We need to collectively articulate a capacity for debating the normative questions. Not just the ethical questions, they're important, very important in here, but the questions more broadly about what are the proper social ends and purposes and needs that investment in knowledge production should be addressing. And should we just be allowing those priorities to be assumed by those who have power already? Or should we be challenging and questioning those? So, well, no, maybe there are actually more important social needs out there for which we could develop this new knowledge. Just to give an illustration of one thing that I've been involved with a colleague in an NGO, a non-governmental organisation, a so-called think tank called Demos in London. This is in the field of nanoscience and technology. We collaborated with a nanoscientist at Cambridge University, actually close to my original field, in fact, but 30 years or so further advanced in terms of nano research in materials science. But they took part in a workshop in Africa. Whereas most nano research and development is funded on the assumption that this is about developing better sensors for better security or for better military technologies and devices, for greater control over populations and terrorists and goodness knows who. We said, well, what about asking a new question? What about if we put the scientists together with people in Africa who do not have adequate water supply? A very basic human need. There are many millions of people in Africa who don't have clean water. So how might nano research, a new cutting-edge field of science, how might nano research be done and developed differently if that kind of social question was in the mind of the scientists doing it and the funders funding it, than the imaginations of the usual kind about big technologies, commercial technologies, things which will sell in rich markets and will be available to big corporate funders and patrons, including governments and military patrons and so on. Let's place a different imagination of human ends and human purposes and human needs in front of scientists and see where it leads. And this is still this is an experiment. We don't know where it will lead. But we think it's a worthwhile experiment. And actually so do the scientists who are doing it with us in this process. And the same kind of question can be asked in the domains of genomics, which CISAGEN is more directly involved in, although we're actually increasingly exploring research in that field of nano-bio interaction. And there's a new field which is called nano-bio-info convergence, which is about where nanoscience, bioscience, and information science, cognitive science, neuroscience, and so on, actually intersect and converge. And fields like human enhancement, come to mind in this kind of domain. So I'll stop there, and I hope that you've been able to understand me. I apologise if I didn't always keep close to the microphone for those of you at the back. But if anyone would like to pose any questions, I guess we can have some help from our local colleagues with translation if anyone wants to state their question in Chinese or in English.
好，下面就是大家可以提问题了啊。刚才那个同学啊，就提问题。现在这个麦克风好像有一点问题，就声音尽量那个大一点，好吧？也可以用这个，可以先举下手。我先测试一下，刚才最后讲那个 nano technology， 大家听懂吗？
纳米技术。
哦，好 ，we got it。那么在这个讲座里，我先插一下啊，就说其实呢，它还涉及到了很多的一些科学、哲学啊等等这方面内容，估计可能离大家稍微的遥远一点。比如介绍到了法兰克福学派啊 （Frankfurt School）， 还有像这种科学哲学的一些，就是对于科学的这样的一些实证主义的呀，这样一些认识论的这些问题等等，可能离大家稍微远一点。但是其他的呢，就是涉及到的更多是跟我们工科院校的同学呢，都是比较息息相关的。那么大家现在就提问。好吗？勇敢一点。好，这位同学，好，第一个啊。
thank you for your wonderful lecture. And I want to ask Professor Mr. Wynne. I want to ask you why Chinese don't have a Nobel Prize winner.
General question.
Thank you.
Well, I can't. Of course, I can't answer your question. It's an interesting one, and I'm sure. Let me say that I'm sure it won't be long before China has a Nobel Prize winner. But I'm reminded when you ask that question of fields of mathematics which were unknown to Western scientists, Western mathematicians in the Soviet Union before the 1980s, basically because of the language and the cultural barriers. Western scientists did not read Russian. And likewise, they don't read, except for, those Chinese-American scientists and Chinese-European scientists who might back and forth. By and large, Western scientists don't read Chinese either. And you're a big country with lots of your own scientific traditions and capacities, and there are probably fields of Chinese science that are unknown to Western scientists, which are really important, and which could, if they were known, could interact probably very productively with Western traditions in those same domains. I don't know, but I'm just going on a little bit of experience of an equivalent situation in the Soviet Union with mathematics.
Excuse me, you said just now that there exists a contradiction between the public and the scientists, that is, the risky and the benefits. So maybe people will inevitably doubt whether the innovation can be good or can benefit and can do good to their own. So maybe how can your scientists make the scientific research more transparent to public and make the monologue to a dialogue between the public and the scientist, and make the public more aware of the scientific thinking or scientific style? Thank you.
Yep. Thank you. Well, when we stop and think about the sheer technical density of most fields of science and technology that are involved, in the headlines of these public issues, nanoscience or bioscience or whatever it might be, it's completely unrealistic to either expect or wish to have science completely transparent or open to every member of the public. It's just nonsensical to even begin to think that is the issue. So what we need to accept is that there is a huge need for processes of trust, which a lot of the time we just take for granted. I mean, I didn't think when I walked into this building, I didn't immediately think, now, can I trust the architect and the engineer who built this building to make sure that it won't fall on me when I spend 2 hours lecturing and talking to students in this building? It didn't even occur to me as a question. Maybe I should have done. Maybe I can start looking and seeing cracks. But I didn't. And it's worth remembering just how much we take trust for granted most of the time. And so those areas where trust has become a problem are actually exceptions to the rule. The normal rule is that we take it for granted and we just do it in that way. So I do think there are domains where we have to develop these new capacities for asking questions about, well, what are we trying to achieve by doing this? And that is a collective issue, of course. That's a collective democratic issue. And there we can expect wider participation in that kind of debate. And we can also expect that those people who do take part will learn whatever technical elements they need to learn of the relevant science in order to take part in those debates. There's a lot of evidence to show that when ordinary citizens without any scientific qualification develop a motivation to learn a piece of technical science, that they can do so pretty well and pretty fast. They can find the right sources for themselves, and they can learn pretty well and pretty fast when they feel the need to. Just one example, when parents maybe have children suffering from particular kinds of medical disorders, and they then have to interact with medical experts over the condition which their child suffers from and what the best forms of treatment, diagnosis, etc. might be. Social research with such people has again shown that without any background scientific qualification, that those parents have learned very fast, impressively so, because they had a need to learn it. And I think that is often found to be the case. So I think that it will always be uneven and limited. But the debate about social ends, human purposes, human priorities, human needs, is not one which requires a PhD in nanoscience or molecular biology or something like that from Harvard or Wuhan or Huazhong University or anything like that. Valuable though that would be as a qualification.
Well, I'd like to ask you some questions. When I was a senior school student, I read a lot of science fiction, especially on the genes. In the story, many large group of scientists work very hard to research on genes. But to my astonishment, in the end of the story, they created a monster that is a human beings can't control it. Do you think it's ridiculous or it's reasonable and will happen in the future? The second question. Nowadays there are two fashionable nouns called green food and genetic food. Genetic food.
GM, yeah. Yeah.
There are many these food in the market, and many people doubted the security of this food, including me. And when I buy food, I will not buy this food. Do you think it's necessary to consider it? Last, I'd like to ask you a personal question. If there are many genetic food on your dinner table, do you often eat some genetic food?
Yeah. Well, officially, there is no GM food in the UK. But I take for granted that I have eaten lots of GM food. And I don't just mean when I'm travelling in the US, where of course it's widespread and unlabelled and everything. I take for granted that I've eaten plenty of GM food in the UK. It doesn't particularly bother me personally because I don't think that the human health risks associated with GM food are the most important risks. I happen to feel personally that there may well be risks of that kind, but they're likely to be pretty limited, and they're not probably as important as some of the environmental unknowns which we're releasing irreversibly when we release GM crops commercially into the environment. Now, there isn't any evidence of any significant harm in the environment either from GM crops. But the point is that the whole process of genetic manipulation was developed as a kind of shortcut for introducing new traits into crops by inserting foreign genetic materials into the DNA of the crops in question. And it was often said in promotion, in support of this technology, that it was more precise than conventional plant breeding. Now, in fact, there are two processes involved in genetic manipulation. One is the excision, the cutting out of the genetic material that you want for the trait that you think it will provide from the original host plant material. The second step is the insertion of that new genetic material in the new plant into which you want to insert the new trait, whether that's pesticide resistance or whether it's pest itself resistance, like BT maize or BT soya, whatever else it might be. Now, the excision process, the cutting out, is quite precise. But the incision process or the insertion process is very, very crude and very, very imprecise. And a lot of the time they don't know what they've generated by that kind of insertion process. It's very, very crude as a process. But the other point is that all of the genetic manipulation technology was developed since the 1970s, mainly originally in the US, but that was developed to the commercial point on the assumption that the original central dogma, in other words, the simple model of gene, protein, organismal trait relationships, one gene, one protein, one trait, that the GM technology was developed under that scientific belief. And it's only since the turn of the century in the mapping of the Human Genome Project, as I said earlier, that we've understood there is far greater complexity than we had originally assumed. So there are many more variations of protein constellations, protein populations created by given genetic manipulations than we had thought. And that might create all kinds of knock-on consequences which we yet just simply don't know about. So, in other words, there is much greater scientific ignorance than had originally been understood in this process. And the whole point about risk assessment is that risk assessment can only tell you about the things about which you already know. Risk assessment can't tell you about the things for which you don't even know to ask the question. So here we're in a position where, because of pressures of commercialization, which have hugely intensified in the last 20 years, particularly in this field of science actually, that the pressure to convert laboratory knowledge into commercialized agriculture is much, much stronger now than it was. So the pressure to go fast and translate from laboratory to field and then to marketplace and dinner plate and so on is much bigger. And yet we're also identifying more uncertainties as that time goes on. So it's, just because there isn't direct evidence of harm yet doesn't mean to say that we shouldn't be thinking hard about it and being very precautionary as to what we're doing. And also asking the crucial question, when one takes these issues beyond risk, in other words, unknown consequences, seriously, then that logically and rationally raises the question, well, what alternatives are there? And many genetic scientists will tell you that there are perfectly good non-GM ways of using plant genomic science to improve crop selection from existing genetic varieties which exist in normal land races of all of the crops varieties that we use on the face of the earth. Whether it's rice, or whether it's wheat, or whether it's maize, or cotton, or whatever. The genetic variety in the land races of the species associated with those varieties contains all of the traits, like pest resistance, like growth under, water-restricted conditions and so on, that we might want in commercial varieties. And genomic science can be used to improve the efficiency of crop selection in that way without doing any genetic manipulation and transgene transfer at all. So this, in Europe, because of the public protest about GM crops, this new scientific trajectory is being developed fast. And, many scientists are now involved in it, and it's being funded, and it's leading to a whole new trajectory of plant genomics research. And, it has still useful connections with agriculture and crops and so on.
Well, thank you very much for your speech. But I want to ask a question not about your speech.
Yeah.
And as a teacher, you think you should teach your students creativity first or skill first?
Creativity or skill?
Yeah, thank you.
Creativity and skill.
Yeah. I don't think that creativity is probably something to be taught. I suspect it's something that, arrives, as it were, from the side. I think that probably there are conditions under which creativity can be encouraged, but the talents need to be there and the inspirations need to be there first. And I think that the only thing that we can really take responsibility for doing is teaching the skills and allow the creativity room to flourish when it's there.
Thank you.
My question is that why Americans and Europeans are so different, in their attitudes, towards the GM food. And my second question is that I'm still not so clear. Can you provide a summary in one paragraph? What means we can take to build the public interest on science?
What means?
Public trust. Can you provide a summary about probably in one paragraph about what it means we can take to build the public trust on science?
Okay. So two questions. First of all, on your observation about the differences between US and European publics, I'm not convinced that those differences which appear to exist are as great as they appear to be. So, for example, in the case of GM crops, where it looks to be the greatest, that looks to be the case where the differences between US and European typical citizens and consumers looks to be the most acute or strong. There was an American social researcher called Tom Hoban, he was director of something called IFIC, the International Food Information Council, which is funded by the biotechnology food industry in the US. And he did research on consumer and public attitudes towards GM crops and foods in the US. And he did surveys every 2 years from about 1996. He started. And he did surveys every 2 years comparing attitudes in the US. Only US he did this. But I read his data quite carefully a few years ago. In fact, when I was leading a European study on European attitudes towards GM crops in Europe. And one of the things that was very clear, and you can see the data show this, there's a correlation. He asks a question to his US survey populations about how much do they know about the existence of GM food in their supermarket shelf trolleys, you know, the food that they buy on the supermarkets. And he then also asks, in which foods do they think the GM is? Now, when it comes to the common things like soya and maize, corn as it's called in the US, and oilseed rape or canola, then the percentage of US consumers in his survey populations who knew that their food contained GM was small. It was something like 30, in the upper 30s%. And it gradually, of course, over the years, from 1996 until about 2002 when he discontinued his surveys, for reasons which I'll come to, the percentage of his respondents who did know that their food contained GM increased. And interestingly enough, as the percentage of consumers who knew they had GM in their food increased, the numbers who accepted that decreased. Now that's interesting. It doesn't prove anything, of course, but it's an interesting thing that perhaps the apparent acceptance of GM food in the US is based upon the non-labelling of, there is no labelling in the US for GM food. So people aren't aware necessarily. Yeah. And the other thing is that when he asked, in what food do you think that the GM actually is, they didn't say soya, maize, canola, which are the three main things. They said more kind of esoteric specialist kinds of vegetables. So they got that wrong as well. They weren't informed in that sense about the existence of GM. But also, he provided a lot of study findings which the industry and the US Food and Drugs Administration, the main regulatory body in the US for GM food safety, and very much in favour of GM, of course, because it didn't even label in the US. But he provided many survey findings which appeared to support the industry and the government policy pro-GM. But when I looked at some of the questions which he actually contained in his survey, questions he asked to the public, they were very loaded questions, as we say. So they would contain forms of words which basically led the respondent in the direction of saying, yes, I accept it. I accept the US FDA policy. And in fact, after having been criticised in one US public debate sort of arena, a website, discussion site, he actually recanted. And he basically admitted that he had been providing biased surveys in favour of the industry. And he's since abandoned this IFIC, this institute, and he no longer has anything to do with that research. So that's one body of social research which the industry and the government were using to say US consumers all in favour, they all know about it, and they're all informed acceptors of GM food. And they also then criticised the European publics for being ignorant, and that's why they were opposed. But the other thing that we found when we were completing our European study in 2001 was a small study which had been carried out by the Consumer Safety Division of the Food and Drugs Administration. And this was a small team of researchers who'd used methods similar to our study in Europe. In other words, open-ended focus group discussions with groups of 6 or 8 citizens. selected in various ways. But they were able to ask in that kind of setting, well, what's your concern about GM crops? In fact, the first question I asked was, do you have any concerns about GM crops in the US context? And the first question that people came up with was very similar to our European one, which was that we don't want labelling. We want labelling of GM crops, but we don't want it for reasons of nutrition, to tell us what the nutritional effects are of GM as against non-GM. We want it because we don't want to buy GM, because we think that there are likely going to be unpredicted consequences that existing risk assessment has not identified. So in other words, they've thought that their main concern was about unpredicted long-term effects of GM crops on the environment, which risk assessment is not able to address, because they don't even necessarily know what are the right questions to ask in the risk assessment. And this wasn't a representative sample, of course. That's an important caveat here. It wasn't a representative population in these surveys. Small scale, non-representative. But it was typical. And the typical response that was coming through from this US study was US publics seem to be just as concerned as UK ones. They haven't mobilised, of course, because, the US context is very different. But it doesn't mean to say that there aren't concerns which exist. And as we know, behaviour can't be taken to be an adequate representation of attitude, which is how scientists often like to see it. That, if they buy it, they like it. That's the belief that scientists have, or would like to have. And I've had British scientists tell me this, your research might be very sophisticated on these attitudes and so on, but if they buy it, they like it. And that's behaviourism as a human philosophy. That's behaviourism, nothing more. Stimulus response, and I don't accept that.
Yeah, I think that we can provide one example is that I talk in the seminar. Yeah, I enjoy to have a car, but I think that it's bad to have many cars in the country because.
In order to rebuild the trust of the public.
Sorry, no, you just reminded me. I didn't answer your second question, Chen, about this question. Are you reminding me to answer that question? Can I answer your second question? Because if you remember, Professor Cheng asked. Yeah, but can I just? Yeah, but Professor Cheng asked me a question earlier, which I evaded. That's good. Yeah. Professor Cheng asked me, if you remember, now 15 minutes ago, what would I do to create or restore public trust in science? Well, one of the first points I'd make is that I think it's wrong to assume that it's right to attempt to do anything to generate public trust. Because if you think about that, then trust is a relational question. Trust is a question of the quality of human social relationships. And if you attempt to do things in order to actually make the other person trust you in a relationship, then by definition, to me, my understanding of trust you've destroyed trust because you've made it an instrumental relationship. You're attempting to control that other person and their response to you. Now, how can that be a trust relationship? I don't think it can. So, I would say that the only thing that we can do, the only thing that we can control, is not the reaction of the other person, it's our own trustworthiness.
Yeah, so
that's the only thing that we can take responsibility for. We can only act in a trustworthy fashion or an untrustworthy fashion, depending upon how we act. If we want to generate trust, we can never guarantee it. All we can do is act in a trustworthy fashion and then hope that others will understand that and trust you. Now, to trust is not necessarily to agree with someone. There might be honest, legitimate disagreement, but there could still exist trust.
So, basically you mean that you improve your own behavior?
Yes. At least ask questions about it.
好，后面那个同学刚才。
In China, the things are different. You know that ordinary people, especially in a rural area, they do not concern such issues about as junk food or nuclear power. So they don't know much about science. So instead of trusting science, they become somehow superstitious about science. So they can't decide whether a thing is true or not. So for these people, what do you think about their attitude towards science?
There's quite a lot of interesting work which has been done on the ways in which there's a paper which was published by somebody called Kenneth Daly in about 1972, and it's called The Spectres of Technicism, and it's basically about the ways in which ordinary people are disoriented by expertise in society around technology. So technological expertise, for example. How ordinary people become disoriented because they're uninformed, they're given contradictory messages, and they don't know who to take seriously or believe or trust. And they've got no basis for actually establishing a judgment of their own. Now, one of the things that very often that we've found in our research is that when, for example, sheep farmers in Britain were affected by the Chernobyl radioactive emission in 1986, the fallout of radiocesium affected their sheep, and their sheep were restricted from sale and consumption, and their livelihoods were very badly affected. And they were told by the scientists initially that there would be absolutely no problem from this. So the farmers were confused. Their initial instinct was to trust the scientists, and then they found that they were severely economically harmed by the advice which the scientists gave them. So they developed serious mistrust of the scientists. But one of the things that when we explored with them the basis of their disbelief, one of the things that was very powerful to see was the way in which they used what you might call the institutional track record of the scientists that they were encountering as a basis for judging. So that when you feel that you have to make a judgment about whether or not to believe in or trust a scientist or scientists making statements on behalf of whichever body it might be an industrial corporation, it might be an environmental NGO, it might be a government department, or whatever it might be. The first perfectly reasonable question which ordinary people ask is, well, what's their track record? Do they have a track record of honesty, of competence, of trustworthiness? Or do they have a track record of the opposite, of untrustworthiness? And that's the first basis on which they attempt to make their judgments. Now, scientists react to that by saying, well, that's nonsense. That's nothing to do with science or the evidence that we define as the evidence. But for ordinary people in their life situations, that is perfectly salient evidence on the basis of which to decide to trust or not to trust. So what you describe as superstition on the part of rural populations, say traditional farming communities or people of that kind, in responding to modern technologies, whether it's GM foods or whether it's nuclear power, whatever it might be, what looks on the face of it to be superstition, very often I think it needs digging down carefully deeper to see what are some of the other implicit constraints, conditions and frameworks within which people are making sense of the situation that they have to deal with. And the evidence that a scientist would say is the salient evidence may not be salient to them. They may have a different world that they're actually trying to live in and sustain. Different relationships, different conditions. And then, if we were to understand those properly, we might understand better what looks on the face of it to be just superstition and irrationality and so on. I think I saw two, so could I see two? Okay, well this guy's been waiting for a while. I've just got one more question, I'm afraid.
When you said you want to rebuild the trust of the public in science, what do you think the role that media plays in this process? You know, the media is very powerful today. Do you think it is very necessary to have a good relationship between the scientists and the media? And also, it comes to the problem of the government, because we all know the media and the government have a very special relationship. What kind of role do you think the government is playing in this process?
就是您是媒体和政府应该在这个建立信任的当中扮演一个什么样的角色
？Two very good questions there. I mean, first of all, on the media, the very word media suggests neutrality. It's a medium through which information flows from a source to a receiver. And the medium itself is just like the medium. And that is the way in which the media themselves like to think of their role. The so-called fourth estate, acting in the public interest to inform democratic citizens about things. And that is very much, I think, the self-image. Certainly the British media that I know, that's the self-image which they will, that's the way they represent themselves and will talk about themselves as operating. But I think there are all kinds of biases in media representations of the issues that we're talking about this evening. Sometimes they take the form of deliberate campaigns, so that some of the British newspaper media, for example, when the GM controversy was at its height, maybe 5 years ago in Britain, the Daily Mail, which is a daily, what we call a tabloid newspaper, a popular newspaper, conducted quite a colourful, extreme campaign against GM crops in order to try to increase its sales. It's quite a straightforwardly commercial thing, you know. We will sell more newspapers if we beat the government with an anti-GM position. And they did it in a very calculated way and quite a creative way in terms of the headlines that they invented and so on. But that's one of the kinds of biases, is that they are commercial outfits and they are doing their best to sell more and to compete with other outfits. But there's a bias, I think, of a more structural kind, which occurs in even the more, what we call upmarket newspapers, the better quality newspapers, in Britain anyway, which I could explain it as follows. The journalists and the editors that you speak to dealing with science very often feel that they are doing their job for the public, in the public interest, if they are exposing conflicts or dissenting views which have been concealed by the official processes. So that they want, in the public interest, to bring into their reports a position for and a position against. And then they'll say, we've presented this to the public and this is in the public interest. But what they also often build into those accounts is an implicit assumption that one side or the other of this conflict is right and the other is wrong. And that one side or the other is biased or is incompetent. So they might be biased by something like, say, being paid by Monsanto secretly for their scientific advice in favour of GM crops. And they present their evidence and their advice as if it's neutral and impartial when it isn't. And the media see it as their role to expose that kind of hidden interest, if you like. But the problem is, I think, that often when they do this, they are designing and writing their stories as if once we have exposed the hidden interests of that kind, or the incompetent scientists who have been playing a role as if they were competent and qualified in this domain, that the singular truth will then be revealed again. So there's conflict, yes, but there is actually behind that conflict a reality of a single truth. And then science will be able to tell us what the answer is on something like GM crops or nuclear power or MMR vaccine or whatever else it might be. And I think that is seriously problematic, because in many of these cases it is not as simple as to say, well, science can tell us what the single answer is. Should we or shouldn't we adopt these technologies? And I think the media plays a role in generating a certain kind of misunderstanding of these issues in that way. Do we have to stop there? Yeah, okay. Yeah. Well, I'm sorry that we have to draw this session to a close. I'm really deeply grateful to you for conducting this session in English language. And I'm also deeply impressed at the quality of your questions, which indicate that you understood an awful lot of what I was saying, which wasn't simple. And it was also lengthy. So I just want to express my admiration as well as my gratitude to you for this evening's discussion, and say thank you very much. Thank you.
Yeah, take one.
I like it.